Okay, so we left off talking about surface tension, which was a result of the first special property of water, which is cohesion, the ability of water to hydrogen bond with other water molecules in forming weak bonds that actually give water some strength collectively. It's what allows this water strider to seemingly walk on water and also allows drops of water to kind of, create that drop effect. It's also what makes belly flops really painful. It's why, cliff divers have to be pinpointed when they enter the water. If they're at all flat, and you've probably experienced this yourself in the past, it can really hurt and feel like you're hitting cement instead of water. And that's because of those hydrogen bonds creating that surface tension. The second special property of water is the fact that water can moderate temperature quite well. And as a result, because we are the water planet, it moderates our climate. So we are going to get into a little physics here, but I promise it's not too difficult. So there's different types of energy out there, and the most common type of energy is what we call kinetic energy, or the energy of motion. And this is something that's inherent in all matter. Atoms are in constant motion because their electrons are whizzing around their atomic nucleus at almost the speed of light, pretty much, and that creates jiggles in the atoms. Even in something that's seemingly solid, there's still movement or kinetic energy that make up the matter, the atoms in that, solid desk, for example. Heat is a type of kinetic energy, and kinetic energy, the more movement there is, the more heat there is. Heat is a measure of kinetic energy that's specific to a volume. Temperature is just the intensity of the heat regardless of volume. So it's kind of like a measure of that heat energy, but it doesn't depend on how many molecules are in, a swimming pool or a pot of coffee, right? Obviously, if there's a lot of molecules in a swimming pool moving around, you're going to have more energy in that swimming pool than you are in a pot of coffee. Although that pot of coffee can have, be high temperature, because there's not as much volume of water molecules, the energy isn't as great, the amount of energy that's being stored in that volume. This brings us to something called specific heat capacity. Because of water's hydrogen bonds, water can hold a lot of heat energy before its temperature increases or decreases. What this means is essentially you just need to put more heat energy into a given volume of water to break those those hydrogen bonds and get them to go into water vapor, for example. So remember, individually, hydrogen bonds are weak, but collectively they're really strong. Remember the surface tension example, right? And so when you have a high volume of water, like our oceans, you can hold a lot of heat in the ocean without it changing temperature too drastically. But when it does change temperature, that means there's either a big increase in the heat or a big decrease, like a big release of heat. And so this is what moderates coastal climates. As a great example, you can see this is Southern California, and this is a summer day in Southern California. And the Pacific Ocean is 68 degrees. And you can see all the coastal cities are around 70 degrees. But inland, far away from the water, you can see it's much hotter. The reason is because the heat that's coming down from the sun is being absorbed by the ocean, keeping these coastal climates very moderate. So there's less temperature fluctuations. Where there's no body of water, that heat heats up the air and causes higher temperatures. And at nighttime, there's less of a temperature change in the coastal cities, but a greater temperature change in the desert cities. It'll probably drop 20 to 30 degrees by the nighttime out here, and less so, maybe 10 degrees in the coastal areas. So a second property of water is its ability to hold and release large amounts of heat, all because of those hydrogen bonds. A third property of water is the fact that solid water is less dense than liquid water and floats on top of the liquid water. Now, just a recap on density. Density is the amount of atoms in a particular physical state. So it's the mass of those atoms divided by the volume that they're in. And so here we're measuring density as grams per centimeter cubed, which is a measure of volume. And for different substances, you can see that water is more dense than ice. And you can see, like, metal elements are much more dense, which all that means is you can put more atoms in that same volume compared to like water or wood or even air, for example. So ice floats because solid water is less dense. Now, when water freezes, what happens is the hydrogen bonds, represented by these dots here, hold the water in a crystalline structure farther apart, each water molecule, than what can be in liquid water. So you can think of it as like the liquid water molecules can get closer, meaning you can have more of the liquid water molecules in a volume of water compared to when it's ice. This is also why if you've ever like taken a can of soda and put it in the freezer and forgotten about it, it explodes because ice expands. It expands when it freezes. The most dense that water can be is liquid water at 4 degrees C. This is the most dense. Things with lower temperature have less kinetic energy and they can pack more tightly, essentially. Solid water is next. Gaseous water, or water vapor, is the least dense. And this is not usual. Usually from density, we go solid, liquid, gas. But for the water molecule, it's liquid, solid, gas. And finally, the fourth special property of water is that it can dissolve lots of different substances. Of course, those substances have to be polar as well because they have to be able to interact with the water molecules. So water makes a great solvent. It can dissolve salt, it can dissolve sugar, it can mix in vinegars, alcohols. It cannot mix with fats like oil because fats are non-polar molecules, whereas water is a polar molecule. So that's why oil and vinegar salad dressing does not mix. So just to recap, water has these 4 super specific and special properties that help make life on Earth possible. The cohesion and adhesion of water allows water to climb against gravity all the way through plants. The moderation of temperature is what keeps our climate livable on this planet because we are the water planet and our oceans can absorb a lot of heat and also release heat to keep temperatures livable. The fact that solid water can float means that our oceans don't freeze into big ice cubes or our lakes don't freeze. So this allows for life to persist even during winter or up in the polar regions. And finally, water is a great solvent because of its polarity. And the reason why water has these special properties is all because of those hydrogen bonds between water molecules. So that's your chemistry lesson on water. But now let's talk about seawater. How's it different from pure water? And of course, your first answer is probably the fact that it's salty. It's not just salty, it has a ton of dissolved ions or other elements in it. Chloride and sodium, the salt part, make up the majority of it, but there's also tons of other types of ions that are dissolved in seawater. Salinity is the measure of salt dissolved in the water. It's measured in parts per thousand, and the average ocean salinity is about 35 parts per thousand. Essentially what this means is if you take 1,000 grams of seawater and you let it completely evaporate, afterwards you'll have left over about 30 grams of salt that are solid and have stayed. We measure salinity by testing conductivity, which is just the ability of a substance to conduct electricity. And so because these are ions that are charged, electricity can travel through them. So salt water is a good conductor, and conductivity can also help us measure salinity. It's worth noting that the ocean has all these dissolved minerals and elements in it, and the ratio of those molecules that are dissolved in seawater is constant. The salinity of the ocean is pretty much the same no matter where you go, but there are some examples where this can deviate, right? And you could probably think of some areas, especially where streams or rivers are flowing into the ocean. This is going to be a lot of fresh water mixing with the seawater, and that's going to decrease salinity. Estuaries are a great example of the interaction between fresh and salt water. Shallow seas, on the other hand, because they're shallow, water's evaporating a lot more, leaving salt behind. So this is where salinity would be increased, like in the Dead Sea, for example. River mouths, as mentioned, just like estuaries, lots of fresh water, this would see a decrease in salinity. Water has a cycle on this planet. Because it exists in all three physical states at the same time on our planet, it's recycled, right? This is called the hydrologic cycle. This is probably something you learned in like 4th grade. But it's super important for our climate. Water is basically the rain we get comes from the ocean. So the sun beats down on the ocean, water evaporates. When it evaporates, it goes into the air as water vapor. When it rises, because it's warm from the sun, it basically meets colder temperatures at altitude, and it condenses into clouds. Eventually, there's so much condensation that the water gets heavy and it falls out of those clouds as precipitation or rain. That rain, if it falls over land, can either get soaked into the land or it can collect in rivers and streams and then run off the surface of the land back into the ocean, and the cycle is repeated. That is the very basic idea of the hydrologic cycle. The amount of water that is on our planet is the amount of water that we've always ever had. It just changes where it is and what physical state it's in over time, right? Think about the windward side of our island versus the lee side of our island. The trade winds blow over the ocean, evaporate the water, it rises, makes clouds, hits our mountains like the Ko'olaus, gets cold, comes back down as precipitation. That's basically the hydrologic cycle in a nutshell on the windward side, right? Because temperature and salinity vary, they can affect seawater density. Cold, high saline waters tend to be more dense. And this is how we measure that. This is an instrument called a CTD for conductivity, temperature, and depth. What it does is it measures the conductivity, i.e. salinity, and temperature at different depths in a water column. And here's the data that it provides. What you can see up here is the percent salinity and the temperature with depth. And this red line shows the temperature having what's called a thermocline, a great change at the shallow waters, so a zone of large change, and then it drops down to a stable temperature in the deeper waters. Here, our salinity tends to increase with depth, increase in density, and you can see that here. The yellow line here shows density at low latitudes like us in the tropics, and in the red shows density at high latitudes like polar regions. Not much change, a lot more change with depth because it's much warmer in the shallow parts.